Hello, I am Anith Nelleri from School of Electronics Engineering, VIT Chennai. Now we discuss on digital holography and its applications in three-dimensional information processing. In this, we choose a particular application of 3D object recognition using digital holographic technique. Digital holography is a computational imaging technique and termed as coherent optics of 21st century. Before getting into the topic, we will see the difference between conventional photography and holography, and then the advantages of holography in 3D imaging. Now let us see how image is captured in conventional photography. Consider an object, three-dimensional object. Let us denote it by O e raised to I phi, where O is the amplitude and phi is the phase information. Phase means the phase information contains the 3D information. When we photograph this object using a camera, digital or analog, whatever, or a photographic emulsion, the process is O e raised to I phi modulus square, because all detectors are square law by nature. So we call it as square law detectors. When this operation is done, what we get? O e raised to I phi into O e raised to minus I phi. As a result, the star also. As a result, this becomes O star, nothing but O modulus square. So square of the amplitude, that means conventionally one is able to record only the intensity distribution or the average intensity distribution. Inherently, the phase information is lost. That means the 3D information is lost in conventional photography. Now the question is how we record this three-dimensional or phase information of an object. Holography gives the solution for this problem. In holography, you have an object, three-dimensional object, which can be denoted by O e raised to I phi, where O is the amplitude information of the object and phi is the phase information or 3D information, which is falling on a detector or a photographic emulsion, and which is superposed with the reference wave. Let me denote the reference wave as R e raised to I delta. So here the fringe pattern or superposition of object wave and reference wave are detected by the detector. Now detector is again a square law detector, but what it detects? Superposition O e raised to I phi plus R e raised to I delta, where delta is the phase of the reference wave. Again, square law detection. So what we get? What we get is that when we expand this, O square plus R square plus 2 cos phi minus delta. So the fringe modulation is done as a function of this. So which contains the phase information. Somehow we are able to retrieve this object wave phase. We can get back the 3D information. But in previous case, what happens? This phase information is lost. Now, with the help of superposing the object wave with the reference wave, we are able to record the phase information of the object wave as a fringe modulation. We have seen the difference between conventional photography and holography. How an interferometric method can detect the phase information, which is not possible in conventional photography. Holography was invented by Dennis Gabor in the year 1948, and he won Nobel Prize in the year 1971. Gabor did inline holography. Later on, Leith and Ubandik in 1962 used laser light to record holograms in a special geometry called off-axis technique. Later on I will discuss about the off-axis method, what are the advantages and disadvantages of off-axis holographic recording technique. On a whole, hologram records the wavefront, that is, complete information of a wavefront, which includes both amplitude and phase. Phase contains 3D information. After the invention of lasers, holography is performed with the help of lasers. Now we will see the recording and reconstruction procedure of a holo. The schematic is shown in the figure. Consider an object. Here it is a cube. It's a three-dimensional object. Illuminate with a coherent laser. A coherent laser illuminates the object, and the light diffracted by the object goes to the holographic plate, which is a recording material, silver halide emulsion. And a reference wave, which is a plane wave, which is also moving in this direction towards the holographic plate. The object wave and the reference wave, they interfere in the photographic plate. So the fringe modulation is captured on the photographic emulsion. This is the process of recording a hologram. And develop the transparency. So this is the photographic emulsion. So develop the transparency. So a wet chemical processing is involved, and replace it exactly where it was kept earlier. And now we don't have object. Illuminate with the exact reference wave so that the light gets diffracted from this hologram plane and the waves converges in various directions and form virtual image and real image. Virtual image. This is virtual image and this is real image. And this is the landmark work by Gaber, and this is reported in a new microscopic principle published in Nature in 1948. So this is a very classical process of recording and reconstructing the hologram. Now, holography goes digital. So that version is called digital holography. They already said, which is termed as coherent optics of 21st century. In this, only difference is, previously we have a photographic emulsion with silver halide plate. Now this is replaced by a charge coupled device, CCD or CMOS. Similar way, the coherent illumination is there, illuminate the object, light diffracted from the object, scattered from the object, and the reference wave, they interfere at the CCD plane. This is a lensless recording scheme. There is no lens in the camera. It's only a sensor, pixelated sensor. So the digitized hologram is stored in a computer. I'll explain the process once again. A three-dimensional object illuminated by a coherent wave, light wave, laser light, light scattered from the object, and the reference wave, which is made from the coherent illumination itself. There are some schemes. I will explain that schemes in the later section. They interfere at the CCD plane. Instead of a photographic emulsion, we have a CCD sensor, which is a lensless CMOS camera. Holograms are digitized and stored inside the computer. The advantage is the wet chemical processing of the film is not present, directly captured by the CCD sensor, which avoids the wet chemical processing. That is the first factor. And once the information is available in the digital domain, computer domain, one can easily exercise the numerical computation process. We don't have to do an optical experiment to reconstruct the hologram. Rather, we can simulate that process using the computer. So numerical computation. That is the reason why we call digital holography. So there are ones which gives the freedom of developing a numerous algorithms with a good amount of perfection. So these are the advantages. Hologram detected by a CCD or a CMOS sensor. Nowadays CMOS sensors are very cheap, high resolution CMOS sensors available, and numerical reconstruction is done using computer, exercised using computer, which avoids no wet chemical, wet chemical processing is avoided, and it's a fast electronic recording, nearly real-time recording. Since the vibration or relaxed system stability requirement is only needed, by improving the recording geometry and by arrangement, one can improve the resolution of the system. And one can, in previous case, this is when a hologram is reconstructed, that happens in the real time, the real space. But here, when the hologram is reconstructed, we have digital information. Both amplitude and phase are available in the computer. So one can process this 3D information. So hologram is a 2D image. Once you reconstruct the hologram, we get two-dimensional complex image. I'll discuss the reconstruction process in these subsequent slides. And after reconstruction, what we get? The complex image, which has a form, which has as I told, after reconstruction we have complex image, which is of the form A plus IB. So tan inverse of B by A, imaginary part by real part, gives the phase information of the object. So that phase contains 3D information which can be used for further processing. So 3-dimension vision systems can be developed because we have 3D information in the computation. So since this is a 2-dimensional image which contains 3D information, 2D image processing algorithms can easily applied for 3D information processing. This is what the scope of discussion in this session. And these are the landmark papers. Professor Goodman and Lawrence demonstrated this. It's a digital image formation from electronically detected holograms. Later on, Carnot, Jaroslawski, reconstruction of hologram with a computer. So it's again here it's a computational reconstruction again. And Shannon and Jepner did it with a CCD. Optical holograms are detected by a CCD or CMOS sensor, lensless CCD or CMOS sensor, and subsequently doing the numerical reconstruction, which enables the phase information in the computational domain, and which is a 2-dimensional image. With that information, one can have 3-dimensional information processing. In order to record holograms using CCD sensor, one important criteria to be satisfied, that is sampling theorem. Hologram is a fringe pattern which is basically formed by the interference between object and reference wave. So basically a fringe pattern. So the highest frequency fringe should be sampled by at least 2 pixels of the CCD sensor. And the highest frequency, the Fmax, is given by this, which depends on the theta max, where theta max is the angle between the interfering object wave and reference wave, and lambda is the wavelength of light used. Delta is the pixel pitch of the CCD sensor. Once again, Fmax is equal to 2 by lambda sine theta max by 2. Fmax is the highest frequency fringe. So this will ultimately impose a restriction on the dimension of the object, because if you want to use the complete spatial bandwidth of the CCD sensor, the interference angle should be less than lambda by 2 delta. So there is an angle limitation which ultimately put a restriction on the dimension of the object that can be recorded using a CCD camera, and thereby the resolution of the image reconstructed. In this section, we will see how a digital hologram can be modeled mathematically. When a hologram is detected by a CCD sensor, we can call it as electronically detected hologram. Optical holograms are detected by a CCD sensor. So fringe pattern is sampled by the CCD pixels. So when light falls on the CCD pixels, each pixel will do a charge integration and gives a number out. So that will comprise an image, a digital image, real value digital image in the computer and can be stored. In order to understand this, we will see the CCD sensor dimensions. A CCD comprising of n cross m sensors of micron dimensions generally, where it is arranged like this: n pixels of delta psi pixel pitch in the x direction, m pixels of delta eta dimensions in the y direction. So totally n cross m pixels, delta psi and delta eta are the pixel pitch. And there is a number alpha and beta which belongs to, or which the value lies in between 0 and 1. This is the fill factor of the CCD array. So this is the diagram. This is the diagram of the CCD sensor. And each pixel, optical hologram, when falls on this sensor, each pixels will integrate the light in this corresponding region and gives a number output. According that, also, the total digital hologram can be modeled like this, where H dash is the light integration process or the charge integration process happens in the CCD sensor, where H1 is the interferogram, optical interferogram falling on the CCD sensor, and then there is a charge integration on each pixels, and how we put it into the m cross or n cross m raster. And this can be represented by the Racht function, the pixel level, and comb function, repeated structure. Once after detection, the digitized real valued images are stored in the computer. They are digital holograms. Now let's see how the numerical reconstruction of digital hologram is done. For this, I begin with the formation of digital hologram. Let's say object function O is equal to O H e raised to I phi 0, and reference wave function R is equal to R H e raised to I phi R. Now the IH is the hologram. The hologram function is proportional to this superposition. So O plus R or the border square. That is what the IH. Rather, I should say it's proportional. IH is proportional to OH square, RH square, 2 OH RH, where phi 0 is the object wave phase and phi r is the reference wave phase. So the relative phase has been recorded as an object, as an fringe modulation of the hologram. So this is the hologram function. So we can see this is the hologram plane, and object plane lies here. So object waves are traveling from xy plane to hologram plane, which is denoted by coordinates psi and eta. Psi and eta. And object to hologram plane propagation of light is modeled as the Fresnel transform of the object function. Object function, the propagation is equivalent to Fresnel transform. An object function at xy plane is Fresnel transform, so that get the propagated wavefront at the hologram plane, and it is interfering with the reference wave. So the Fresnel transform of the object function interferes with the reference wave and forms the hologram. And there is a plane where is the image plane. After numerical reconstruction, we have to go to a image plane, which again involves another Fresnel transform, where you get the reconstructed image, that is the image plane, reconstructed image from the digital hologram. But here hologram is a real valued function, but once after reconstruction you get a complex image which is denoted by coordinates x dash and y dash. So this can be understood by a Fresnel approximation method condition or rectangular approximation. If it validates, the condition is satisfied, that is distance between the object plane. Suppose d is the distance between object plane and hologram plane, and d dash is the distance between the hologram plane and image plane. Then there is if the Fresnel approximation holds good, you can do a rectangle. Then object plane and hologram plane and image plane can be connected by the Fresnel transform, a mathematical transform. This is the continuous representation of the Fresnel transform. Now, the reconstruction process is done like this. The hologram function multiplied by the reference wave, which is used for recording. Hologram is the real value digital image multiplied by the reference wave, mathematically modeled reference wave, which is same as the reference wave what is used for recording, and then do a Fresnel transform. So the previous case we have seen, it's a continuous transform. This is a continuous transform, but here in order to apply it numerically we have to discretize. After discretization it takes the form. In summary, this is the detected digital hologram multiplied by the mathematically modeled reference wave, and then do the Fresnel transform. It's a mathematical transform, and the Fresnel transform can be implemented using fast Fourier transforms, FFT transforms, where delta psi and delta eta are the detected pixel dimensions and detected pixel dimensions. And after reconstruction, so hologram has got pixel dimensions same as that of the CCD dimensions, and total number of pixels depends on the total number of the total number of pixels in the hologram is equal to the total number of pixels present in the CCD sensor, and the pixel size dimension is same as that of the CCD pixel dimensions. But after numerical reconstruction, we get the image, that is a complex image with pixel dimensions that can be computed. Delta x dash and delta y dash may be computed in this fashion. Like conventional holography, one can record digital holograms in both inline and off-axis geometries. First, we will see the inline holographic schemes. The reference wave, object wave, they interfere in inline. That means there is no angle between object wave and reference wave. So while reconstruction, what happens? The reconstructed image, that is this terms corresponds to DC, and the real and virtual images, they are merged together. Whereas in off-axis holography, there is an offset angle between object wave and reference wave. So the reconstructed image, DC, twin image, the real and virtual image and DC, there is a separation between these terms. So that can be filtered off easily. But one problem is, in digital inline holography, one can completely utilize the bandwidth of the recording device. But due to the angle limitation problem, because we are incorporating an angle between the object wave and reference wave, the spatial bandwidth of the CCD cannot be utilized in that extent. But many of the application problem, the resolution achieved in off-axis holography is good. But there are several algorithms to improve the resolution in line and off-axis. How to remove the DC and twin images? There are methods. Since the information is available, the reconstruction process is done using a computer. So you can develop algorithms to suppress DC and twin image. In summary, inline holography, inline digital holography, object waves, there is no angle between object wave and reference wave when they interfere. But in off-axis holography, there is a small offset angle between this. Whether it is an inline hologram or not, irrespective of the nature, whether inline or off-axis, the reconstruction process is something like this. Hologram is multiplied by the reference wave, that is a numerical reference wave, and then Fresnel propagate to the image plane, which is a mathematical transform, Fresnel transform, implemented using computer. If it is an inline holography, these terms will be merged together. In off-axis holography, there is a small separation due to the offset angle between object and reference waves. As I told, there are methods to remove DC and twin image in inline holography. And the phase shifting digital holography, this was proposed by Professor Yamaguchi. In this, a phase shifting technique is used to eliminate DC and twin image. So I'll explain the recording geometry, how the phase shifting is done, and how it eliminates the DC and twin image in this process. So a laser, this is the laser, which reflected by a mirror M1, and after reflection it propagates this direction, and there is a beam splitter which splits the beam into two, one in this arm and other this direction, and again there is a mirror M2 which reflects in this way, and there is a spatial filter. The spatial filters removes the noise in the beam and collimated by lenses. Collimation makes the beam parallel, and this corresponds to the reference wave arm, and one arm object light falls on mirror M3 and get reflected and illuminates the 3D object, and the light scattered from the object propagates towards the CCD sensor, and from the other arm a plane wave which comes and interfere. After reflection from the beam splitter, one part goes to the CCD. So the reference wave coming like this and the object wave which is scattered from the 3D object, they interfere in the CCD camera. So this is something like a Mach-Zehnder geometry. So this geometry is called Mach-Zehnder geometry. So one arm, this is one arm which comes like this and goes to the CCD, and from this light reflected by the mirror, and the scattered light illuminates the object, 3D object, and the scattered light propagates CCD camera. So this acts as a reference wave and this acts as the object wave. They interfere in the CCD camera. In the inline geometry, there is no angle between the object wave and reference wave. So this is called inline interference. But conventionally, when we reconstruct this hologram, what happens? The DC twin image, the images, real and virtual images, and DC, they merge together. So it will be like a noisy image. The question is how we can remove this noise. So in this process, we record four holograms. I1, I2, I3, I4. And from this, how we can retrieve the complex, 3D information without the noise terms. So how we are recording these four holograms, that matters. So the first hologram is recording with zero phase with reference with the same object wave, but introduce a phase, zero phase, no phase, and these two waves interfere and first hologram is recorded. Second, by using the retarder plates or wave plates, by operating simultaneously, introduce a phase shift to the reference wave pi by 2, object wave same as previous, and this phase shifted pi by 2 phase reference wave, they interfere and record the second hologram. And third, by appropriately doing the combination of this wave plates, lambda by 2 plate and lambda by 4 plate, achieve a phase shift of pi, and then that reference wave and this object wave again they interfere and record the third interferogram. And similarly the fourth, by the suitable combination of these retarders, get the phase shift of 3 pi by 2, and then same way the fourth hologram is recorded. This fourth hologram, I4, hologram number I4. So in this process, four holograms are recorded with the reference wave phases 0, pi by 2, pi and 3 pi by 2. The resulting 4 holograms I1, I2, I3 and I4. By this method, I4 minus I2 by I1 minus I3 gives the cosine, the phase value. And take the tan inverse of this, we get the object wave phase. What is recorded at the CCD plane? So if you do an inverse transform to the distance d back, inverse Fresnel transform of this, we get the exact object phase. So retrieve the complex object phase which is free of DC and twin image at the CCD recording plane, and then do a inverse Fresnel transform to get the exact object wave. So this is the method. The phi can be achieved by tan inverse of this. These are the phase shift and do a discrete Fresnel transform. Thus we can get the exact three-dimensional object wave. That is a method in phase shifting digital inline holography. Next we will see the off-axis Fresnel digital holography. This is the technique. A laser which is split into two in this arm and this arm. Light reflected by this mirror M goes to another mirror and illuminates the 3D object. And this, in this arm, it propagates and reflected by this mirror and comes to this, and again there is a beam splitter, and you can see there is an angle. This reference wave reflected by this beam splitter makes an angle with the object wave. So there is an offset angle between the object and reference wave, and object is kept at a distance d from the CCD sensor. So the hologram is formed between the Fresnel transform of the object for a distance d, interfering with the plane reference wave at an angle theta. So the problem is the CCD may not be able to record the complete, or the complete bandwidth of the CCD, spatial bandwidth may not be able to utilize because of this model. But the advantage is, in previous inline holography, all the terms are merged together. But here, after reconstruction, you have separation, DC and focused image and twin image. Here it's a DC, undifracted light, and here it's an defocused and it's a real image. So we can achieve a separation. So noise terms are separated out by introducing an offset angle between object and reference wave. But it is not eliminated. But in phase shifting holography, one can completely eliminate by phase shifting method. But in that case, you need to use 4 holograms. Phase shifting inline digital holography requires 4 holograms. Whereas in off-axis holography, you are recording only 1 hologram with an offset angle between object wave and reference wave, and that will help you to separate the terms, the DC. So when a hologram is formed, object wave and reference wave, they are interfering at an angle. So you have 0 order terms, that is called DC, and image will be there, and there is a twin image, right? So these are the terms can be separated out. And if you want to filter it off before reconstruction process, you can do a Fourier transform of the hologram. So you can decompose the spectrum, and by using filters, only the required, unwanted terms can be filtered off. So this is a hologram. You before reconstruction do a Fourier transform, and the terms get separated, and use an appropriate filter and remove it, and do another inverse Fourier transform. So original hologram, filtered hologram you obtain, and then use that hologram for further processing. That way one can eliminate the DC and twin image present in off-axis holography. So far we have seen two types of holography. One is inline digital holography, off-axis funnel digital holography. Inline, there is no angle between the interfering object and reference waves, whereas in off-axis holography there is small offset angle. In inline holography, the complete spectrum of the object can be recorded. The full bandwidth of the CCD can be utilized. But the drawback is all the terms will be merged. Virtual and zero order terms will be merged and full of noisy. But this can be avoided by phase shifting method. But you have to record 4 holograms to process, and computationally slightly intensive. More information you have to use. But in off-axis holography, you can separate out the terms, and by Fourier processing you can filter off the terms. So these are the different types of holography and processing. And there are several other algorithms you can utilize it for better or improving the results. So this is the typical hologram of a letter E recorded in a Mach Zehnder geometry. The hologram size was 576 to 768. Once you reconstruct the hologram, the image will be like this: DC, focused image and defocused image. And this is the higher order diffraction terms. These are all higher order diffraction terms. And these are all noises. One can be filtered off. So the recording parameters used, the distance between the letter E from the CCD camera is D, and the wavelength used was 532 nanometer, and the CCD pixel size, the square pixel delta psi and delta eta are same, that is square 6.7 micron, and this was used in the off-axis geometry. Approximately the angle of interference is 1.6 degree, so that we are able to achieve a separation between the real and virtual images and the DC term. Now, when the same hologram, the digital holography allows to improve the algorithm, because the reconstruction process is exercised using a computer. So one can design their own algorithm to improve the result. So previously we have seen an algorithm as a direct method of reconstruction of off-axis hologram, and this is the reconstruction. When the same hologram was reconstructed by a different algorithm, which is the nonlinear method proposed by complex wave retrieval method proposed by Labeling et al., which is published in this journal, one is able to get a better result, and all noise, DC, everything filtered off. So this is the scope of digital holography. By developing an appropriate algorithm, one can improve the results, and only specific required information can be retrieved. So when a hologram is reconstructed, we get a complex image. This is the retrieved image at the CCD plane amplitude, and this is the phase of the object. So then from this object plane, information can be retrieved by Fresnel transform, so which is free of noise, so which is a complex image which contains 3D information. So by appropriately processing the hologram, one can obtain very good 3D, noise-free 3D results, and this can be used for further processing of 3-dimensional information processing. We have seen how 3D information can be sensed and retrieved using digital holography. Once the 3D information is available in digital domain, that is in the computer, This information can be used for three-dimensional information processing. In this section, we discuss one such application. Conventionally, the three-dimensional object recognition is done using multiple perspective imaging or combining many two-dimensional perspectives. For this, several cameras are required in various directions. Image various perspectives of the 3D object, and from this information process and get the 3D information. And this becomes computationally intensive because large number of two-dimensional images are to be processed. And obviously this becomes highly complicated. There are a lot of difficulties in implementation and at operational levels. Digital holography can sense 3D information that we have already seen. The hologram contains 3D information. Once you reconstruct, you get digital complex images, that is two-dimensional digital complex images, which contains 3D information. So by applying 2D pattern recognition techniques, we can have three-dimensional object recognition. Since the information is available in the digital domain, one can devise a robust algorithm for processing. Moreover, the object recognition process happens nearly in real-time process. So in this section, we see a demonstration, an algorithm for three-dimensional object recognition and classification. In this, off-axis, the object information is retrieved from off-axis, single off-axis hologram, and the wavelet based image processing can enhance the performance of the correlator, and the object recognition is done by 2D correlation methods of the three-dimensional information. And finally we can compare the performance of classical matched filtering and wavelet based matched filtering technique. So as a first step, we see the recording and reconstruction or sensing and retrieval of three-dimensional object information. Figure shows the Mach-Zehnder geometry, in which a laser which emits a wavelength of 532 nanometer. There is a spatial filter, collimation assembly, which contains pinhole and a filter, spatial filter, which removes the noise in the beam, and the convex lens, that is a collimator, which makes the beam parallel. So we get a plane wavefront out of this. So this is a plane wavefront, and there is a beam splitter which split the beams in various ratios. Let's say 50% intensity, 50% here and 50% intensity. So split the intensity into two, and one goes in this manner and other here, this direction. And this mirror reflects it and pass through the object. This is the object, three-dimensional object. And other serves as the reference wave. So this arm, this is the object wave arm, and this is the reference wave arm. And using this beam splitter, we combine the beam or make them interfere at the CCD plane. As a result, we get a digital hologram. So the interference angle is approximately 1.6 degree. Now we'll see the construction of a three-dimensional object. Here there is a triangle in the back plane and a rectangle in the front plane, and it is separated by a distance 1 centimeter. Light enters through it and exits through this space. So such an object is kept here. So that acts like a three-dimensional object with a depth of 1 centimeter. Record the hologram. Single off-axis hologram is recorded, and by using complex wave retrieval, reconstruct the three-dimensional information, which is a complex image. Now, a matched filtering geometry can be used for object recognition. So, take the reference, record the reference and reconstruct in this manner. And target is also recorded and reconstructed in the same manner. Both are two-dimensional complex images. If one wants to enhance the features, they can use the wavelet filter, and the wavelet coefficients can be matched filtered so that three-dimensional object recognition is possible. Here the mother wavelet, Mexican hat wavelet, is used, and these are the correlation of wavelet coefficients, so that we get a correlation peak, and the correlation peak indicates whether the true or false object recognition is done. If you don't use the wavelet based correlation, the correlation peak is not that sharp, but when you go for a matched filtering, wavelet based matched filtering, the performance improves. And the study shows that the wavelet based matched filtering has got better discrimination capability compared to classical matched filtering. The details of this work can be seen in this reference paper written by Nelleri et al. Digital holography can be used for phase contrast image also. A phase object which is invisible, but still after reconstruction the phase contrast can be obtained. So this can be used for imaging the invisible object. So this is such an object which is a transparent coating, triangle and rectangle. This can serve as an phase object. These coatings are invisible because light transmits through it, and record and reconstruct and generate the phase contrast, and finally by wavelet or conventional matched filtering can be done for three-dimensional object recognition. This is another work which can be referred for three-dimensional object recognition and classification of phase objects. So on a whole, digital holography can record and reconstruct three-dimensional object information as digital complex images. Then this information can be used for various applications. One such application is development of three-dimensional vision system. The three-dimensional information hologram can be transmitted through internet also. So thus we can achieve three-dimensional information transmission through digital channels. In next generation, internet servers may be a bank of digital holograms and numerically reconstruct a hologram. So it's a compression of data which can be achieved using digital holography. This is all about the lecture regarding methods of digital holography and one of its application in three-dimensional information processing. such as 3D vision system development. Thank you.